What is light? Well, you know it allows you to see, but do you really know how? Do you know what causes the shimmering colors in the northern lights, or why we even see colors in the first place? For centuries, scientists around the world have tried to find answers to questions like that. They develop models to try to explain their observations about light. Some early scientists thought that light might consist of particles that enter our eye and make us see. However, when light shines on an object, that object's mass didn't increase. Therefore, light had to be a form of energy instead. But what form? Well, after hundreds of years of observations and experience, scientists haven't found one simple model that explains all the characteristics of light combined. One helpful model for us is the ray model that we'll be learning about a little bit later on. A ray is an imaginary line that represents the direction in which light energy travels. While it explains how light forms images in a mirror and shadows on the wall, the ray model cannot explain colors or the way that light behaves when it travels through a very tiny slit. The wave model explains those characteristics. Within this unit, we're going to be learning how to use these models to help us develop an understanding of how light really works. We're also going to learn how we can use light technologies to assist us in everyday life. For example, an understanding of light has made it possible to develop advanced technologies like lasers used in laser eye surgery or in fiber optics, which are being used significantly more within communications. But as we get started talking about light, let's go back to Scripture. Because Scripture actually deals with light in the very beginning. And I mean that literally. When we start reading Genesis 1, verse 1, we read, "In the beginning, God created the heavens and the earth." And as we go on, we get to Genesis 1, verse 3, which states, "And God said, Let there be light." And there was light. And as we read on, we begin to say that God kind of separates the light from the darkness. And he creates this sun to govern the day and this moon to govern the night. And eventually we read on that God creates all the stars and the heavenly hosts that are all in this grand universe that actually baffle our mind when we start to understand the vastness of it all. When we start to understand that our sun, which by the way is incredibly massive, and without it, life on this earth would not be able to exist. Our sun is a star, and it is a source of energy that is radiating to us in order to allow us to live here. And yet, there are stars in the billions that are in our universe that are bigger than our star, that are bigger than our sun. And God spoke these things into existence and made it happen. And that's incredible. And it really should make us stop and wonder and appreciate the God that we serve. From the beginning, God created light. God also called himself the light. God also told us to be a light in the darkness. And so light has an important theme to play when it comes to the Bible. In the simplest terms, though, in terms of science, light is the form of energy that we can see. The sun, for example, is a natural light source. It's the source of the most abundant and least expensive light in the world. Fire is another natural source of light. The sun is actually a star, as we've mentioned before, and all stars in the universe are sources of light. Light spreads out. Another word for that in science that we use is radiates from the sun and other stars in all directions, like the spokes of a bicycle wheel. This type of energy transfer does not require matter. It's known as radiation, which is great because we don't have matter for that to travel through when it comes to space, which is why this radiation energy from the sun is allowed to travel through space and get to us. Energy such as light that travels by radiation, we sometimes then refer to as radiant energy. Less than 1/10 of 1 millionth of a percent. Let that number kind of sink in. 1/10 of 1 millionth of a percent of the sun's energy actually reaches Earth. That's crazy. We need sunlight and sun energy in order to live, in order to function, in order to do anything. And yet, we're doing all of that on 1/10 of 1 millionth of a percent. Nonetheless, our lives are totally dependent on that energy. Plants, people, and other animals could not live without light from the sun. But because sunlight is not always available, people have developed light producing technologies or artificial lights. A light bulb, for example, is an example of an artificial light source. And like the sun, light from a bulb radiates in all directions. But what else can produce light? Well, think about what happens when you strike a match. Chemicals on the tip of the match react to produce heat and light. Once the chemical energy is used up, the match is no longer useful. And like the match, all other sources of light require energy. Flashlights use electrical energy from batteries. Light bulbs glow when you switch on electricity. The light that leaves the sun is formed through a process called nuclear fusion. Let's get into the first basic principle of light, though. And we've seen that and talked about how light is a form of energy. And this is really that first basic principle of light. When light is absorbed by a surface, it can be transformed into several different forms of energy. Light can be transformed into thermal energy or heat, electrical energy, which we use all the time as well, and chemical energy. For example, the absorption of sunlight by a black sweater causes that garment to gain thermal energy. Think about if you have a black car, for example, or black pavement. When the sun's energy beats down on that, it's going to get hot. Thermal energy. And it's going to be much hotter than something that's white. We'll talk about why a little bit later on. We could also have solar cells that change light into electricity. And we have this, for example, in solar panels all the time. Trees also in our neighborhood absorb sunlight to make chemical energy or sugars, and this is a process called photosynthesis, which we've talked about before as a way of transforming or using light to transform, well, really carbon dioxide into oxygen, but there's a whole other process that allows it to create different sugars to allow plants to grow. The brightness or intensity of light also indicates how much energy a surface will receive. So a surface can absorb more energy if the brightness of the light intensifies. It makes sense. The brighter the light, the more energy it's giving off. For instance, pavement may feel hot to the touch on a sunny summer day. However, the pavement will feel only warm if the clouds block out the sunlight. Then we have less intense light coming through, and so therefore it's going to be absorbing less light because there's less coming through. So now let's talk about some different sources of light. Think about this. How would your life be different if the sun and stars were the only source of available light to you? You would probably go to bed very early, especially in the winter, because there would not be much that you could do after dark. Without artificial sources of light, there would be no TV or screens, no lamps for reading, no computers. All the rooms in buildings would probably need to have windows or skylights in order for us to be able to do anything. But we are lucky to have many sources of light available to us. In earlier times, once the sun had set, people found their way around outside with the aid of torches and lanterns. Candles and oil lamps were commonly used indoors, but imagine trying to study by the light of a candle. Today, we have so much light in our cities that actually light pollution can wash out our view of the skies at night. And this is why many observatories have to be located far away from urban areas, far away from that light pollution to be able to pierce through, to be able to see everything that's out in space without being literally polluted by the surrounding light that would make it harder for you to be able to see. However, some communities are taking steps to conserve light energy. For example, new types of streetlights are designed to direct their light downward instead, so that they illuminate the ground or the street and not just the sky. In addition, these lights are comparatively energy efficient. For example, the yellow sodium vapor lights, so if you have kind of a yellow tint to that light, it could be because they're yellow sodium vapor lights. They're much more efficient than typical white lights. And in the next little bit, we're going to compare different types of light sources, both natural and artificial. And let's begin as we do that with our first source, an incandescent source. Now, an incandescent source, this used to be our main source of light energy, using an incandescent light bulb that was first credited to be invented by Edison, and was used widely up until just a few years ago, where things started to switch over to some more energy efficient light sources. And we're going to see why in a minute, because incandescent sources are actually terribly inefficient at what they do. An object can be heated to such a high temperature that it actually emits visible light. And visible light then ends up being kind of a byproduct of the fact that you're heating it up so much. It gets so hot that it produces a bit of light as a result. Such an object is called an incandescent source of light. The emission of visible light by a hot object is called incandescence. Both candle flames and light bulbs are examples of incandescent sources. In the light bulbs previously used most commonly in our homes, electricity would heat a metal wire filament in the bulb. This filament would become so hot in the middle there that it would glow white. The change from electric energy to visible light involves this energy transformation, electrical energy turning into thermal energy or heat, and as a result, we have a byproduct of visible light energy. And if you've ever touched an incandescent light bulb right after you've turned it off, well, chances are you have possibly burnt yourself a little bit. And that's because about 95% of the energy given off by incandescent light bulbs is actually released as heat. In a way, an incandescent source of light is like having a small electric heater in the room. It was this reason when I was doing some house renovations, when I was taking a look at putting in some lights in my basement at my previous house when it was very, very low, I was looking at different light sources that would not give off very much heat, because I didn't want it to feel like you're all of a sudden under a heat lamp every time you go underneath a new bulb. And the old incandescent sources of light would have been that way. Then we move on and we have fluorescent sources. You may have noticed that when you stand under a so-called black light, some of your clothes actually glow, especially if you have white clothing, like white socks. In this process, what's happening is high energy, invisible ultraviolet light is absorbed by the particles in the fabric. We're going to learn more a little bit later on about UV light, and we've learned a little bit also in our atmospheres unit, in our previous unit. These particles then emit some of that energy as light that you can actually see, making your clothes glow. This glow is called fluorescence. And we can kind of summarize that energy transformation in this way. We go from ultraviolet light energy to energy absorbed by different particles to finally visible light energy. A fluorescent source of light makes use of this energy transformation process. And here's an example of a fluorescent tube light where we see the same sort of thing happening. An electric current from the lead-in wires and electrodes cause mercury vapor inside the tube to give off ultraviolet radiation. So basically, you're electrifying mercury vapors, which give off UV rays, and then a phosphor coating on the inside of the tube absorbs that energy, which causes it to glow, thus producing light that you can see. The energy pathway for this it looks a little bit more complex, but it's the same sort of idea. It's just this time we're starting with electrical energy, which then gets absorbed by the mercury particles, which then turns into ultraviolet light energy, which then gets absorbed by phosphor particles, which then can create visible light energy. A little more complex, but that's the way that that would work. Fluorescent tubes have a few disadvantages, though, compared to incandescent light bulbs. First, they're usually more expensive to make and more difficult to dispose of than incandescent bulbs as well. Also, both the phosphor coating and the mercury vapor in the fluorescent tubes are toxic, which is why you have to be careful if these break. Not that it would be in the amount that it could cause a lot of damage or any big issue if just one of these broke. But when we start scaling that up and when we start talking about fluorescent tube lights worldwide, we start talking about very, very little amounts slowly adding up to a large amount of toxicity. However, if we compare the energy pathways for the fluorescent tube and the incandescent light bulb, we'll notice a definite advantage of the fluorescent sources. And that's because thermal energy is not as much involved in the operation of a fluorescent light source. In fact, you can even sometimes touch those fluorescent tubes when they're lit, and as a result, fluorescent lighting wastes much less energy as heat than incandescent light. So therefore, fluorescent lighting is more energy efficient. So there's kind of a bit of a trade-off that way. All right, now let's move on to the next one. Let's move on to a phosphorescent source. Well, a phosphorescent source is very similar to a fluorescent source. In this case, light energy is absorbed by certain particles that can actually store that energy for a little while. And that's where this is different, is that it stores that energy and then it's later released as visible light, usually slowly over a period of time. The original light energy may be either in the form of high energy UV light or visible light. And the persistent emission of light following exposure to and removal of a source of radiation is known as phosphorescence. So I like to think, for example, of the glow-in-the-dark star stickers that sometimes you might put on your ceiling in your bedroom. And you have the light on and they absorb the energy from that light. And then when you turn the light off, they slowly release that and they glow for a period of time afterwards. The main difference between a fluorescent source and a phosphorescent source is that particles in the fluorescent source release their light energy immediately, whereas phosphorescent particles take longer to emit light. They also continue to glow for a while after that energy source has been removed. Then we move to chemiluminescent sources. Now this one might sound very complex, but we start off with the word chemi, which actually is leading us to kind of understanding chemical, and luminescence just means lighting up. So chemiluminescence deals with chemistry lighting something up, or chemical reactions. So light can also result from the energy released in chemical reactions. The chemical reaction produces energetic particles that give off visible light energy, and this process is called chemiluminescence. The energy pathway for that can be represented using the following. Chemical energy turns into visible light energy. Nice and simple. Glow sticks, often used as emergency signal lights or used kind of for fun at parties, produce light by chemiluminescence. The way that it actually works is in a glow stick, you have a breakable barrier that separates two different liquids, and as you bend it, as you crack it, what you're actually doing is you're breaking that barrier and you're causing those liquids or those chemicals to mix together, which creates a chemical reaction which causes it to glow or release light as energy. Our final source of light energy that we're going to be talking about is bioluminescent sources. Now, again, like we did with chemiluminescence, stands for chemical. Bio refers to life or living things. So living things that give off light. If you were moving through the darkest depths of the ocean in a research submarine, you might be surprised to see glowing creatures swimming past. These animals cannot be incandescent or fluorescent sources. Instead, they rely kind of on chemiluminescence. They rely on chemical reactions inside their own bodies to provide the energy for light. This special type of light produced in living creatures is called bioluminescence. The result is known as bioluminescent source of light. Many organisms that live deep in the ocean use bioluminescence because so little sunlight reaches far below the surface. Some fish produce bioluminescence to attract prey. Certain fungi in caves also produce bioluminescence, as do fireflies. Fireflies actually use bioluminescence to glow to attract a mate. So, all objects that emit light are called luminous. Luminous refers to light emitting objects. But how can we see non luminous objects? Objects that do not emit light? And that's something that we're going to get into in a future video.